Redshift and Reality, Rethinking the Expanding Universe, the Augmented Newtonian Dynamics Theory. The birth of a law, Edwin Hubble and the expanding universe. Until the 1920s, astronomers believed the Milky Way was the entire universe. The faint, hazy spirals scattered across the night sky were thought to be nearby gas clouds, or nebulae, within our own galaxy. The idea that these objects might themselves be vast, independent star systems lay on the fringe of speculation. Then came Edwin Hubble, lawyer, soldier, and soon to be one of the most meticulous astrophysicists in history. Working at the Mount Wilson Observatory with the 100-inch Hooker telescope, the largest in the world at the time, Hubble began photographing these mysterious nebulae. In 1923, he identified Cepheid variable stars in the Andromeda Nebula and proved, beyond doubt, that it lay far outside the Milky Way. With that single discovery, the universe expanded a millionfold. 6 years later, in 1929, Hubble announced an even greater revelation. The light from distant galaxies was systematically redshifted. The farther away they were, the faster they appeared to recede. This relationship between velocity and distance became known as the Hubble law, and its constant as the Hubble constant. It was the first quantitative indication that the universe itself might be expanding. Edwin Hubble was among the most respected astrophysicists of his time, a man whose integrity and meticulousness made his results appear unassailable. An advocate and former soldier, he approached astronomy with disciplined precision, recording his data scrupulously. From an ethical standpoint, few scientists could match his honesty or restraint. Despite his meticulous approach, it was later found that his results were in error by an unacceptably large margin. In 1929, Hubble announced that distant galaxies appeared to recede at a rate directly proportional to their distance and calculated an expansion rate of about 500 kilometers per second per megaparsec, nearly 10 times too high. The flaw lay not in his diligence but in his misinterpretation of Cepheid variables, the pulsating stars used to gauge cosmic distances. It was not yet known that there were two distinct classes of Cepheids, later identified by Walter Bade in the 1940s, the bright, young population 1 type and the older, fainter population 2 type. Hubble's confusion between the two caused him to underestimate galactic distances and, in turn, to overstate the universe's rate of expansion by almost an order of magnitude. The fragile foundations of cosmic expansion. Hubble's discovery was electrifying, a triumph of observation over speculation. But its interpretation rested on ground that was far from solid. The linear relationship he plotted between distance and redshift looked convincing, yet it was based on a handful of galaxies, many of them mismeasured. His distances were wrong by large factors, and the expansion rate he derived implied a universe scarcely 2 billion years old, younger than the Earth itself. This contradiction was quietly ignored in the excitement of the moment. At almost the same time, the Belgian physicist and priest Georges Lemaitre offered a theoretical explanation for Hubble's results. Working from Einstein's field equations, he allowed the so-called cosmological constant to produce a dynamic universe, one that could expand or contract. Using the same sparse and uncertain redshift data then available, he arrived at an expansion rate of about 625 kilometers per second per megaparsec, even higher than Hubble's already inflated figure. The numerical match between his theory and Hubble's observations seemed impressive, but it was largely a coincidence. Both men drew on the same flawed distance scale. In truth, Lemaitre's result was less accurate than Hubble's and rested more on a convenient overlap of errors than on mathematical precision. Ironically, because Lemaitre's original paper was initially ignored, and later, when translated, published without his numerical section, his reputation rose posthumously as the overlooked prophet of cosmic expansion. Modern cosmology now celebrates him as the father of the Big Bang, often overlooking the fact that his early figures were wildly off. What began as a speculative fit between uncertain data and adjustable equations has since become one of the most powerful narratives in science. The cosmic expansion constant, observational foundations. Although there remain severe doubts about the foundations of the expanding universe model, few quantities in modern astronomy have been measured, debated, and celebrated as much as the cosmic expansion constant, and the strongest, most direct anchor comes from space-based Cepheid measurements. high-precision parallax calibrations from Gaia-fixed Cepheid absolute luminosities, the Hubble Space Telescope, and more recently JWST and Spitzer in the Near Eye, then measures Cepheid light curves in nearby galaxies with exquisite crowding control. These satellite datasets tie directly to Type 1a supernovae in the same hosts, building a tight distance ladder that yields a robust result. The ladder is cross-checked with geometric anchors such as megamaser distances, e.g., NGC 4258, and agrees with independent large-scale probes, baryon acoustic oscillations, super Type 1a novae, while high redshift mapping of galaxies and quasars confirms that recession speed grows with distance, implying superluminal recession beyond the Hubble radius as a metric expansion effect. In sum, space-based Cepheid photometry and parallax provide the cleanest, most repeatable foundation under the cosmic expansion constant, with multiple, mutually reinforcing rungs making the empirical case exceptionally strong. The inflationary universe, the standard model of creation. Modern cosmology tells a story of astonishing simplicity and scope. According to this view, the universe began as a singularity of infinite density, a point where space, time, and energy were one. A fraction of a second after its birth, something extraordinary occurred, a brief but explosive episode of cosmic inflation. In this moment, the universe expanded exponentially, doubling in size again and again within less than a trillionth of a second. This idea, first proposed by Alan Guth in 1980, was not meant as a grand metaphysical statement but as a practical solution to several troubling puzzles in the Big Bang model: why the universe looks so uniform, why its geometry is nearly flat, and why we see no magnetic monopoles. Inflation, as Guth described it, was simply a phase transition, a release of trapped vacuum energy that drove a fleeting, ultra-rapid expansion before settling back into normal physics. But as decades passed, the idea of inflation grew far beyond its modest beginnings. Successive generations of theorists extended it to explain not just the early smoothness of the cosmos but the entire accelerating expansion we observe today. What began as a technical adjustment became a sweeping narrative, the universe expanding faster than light, slowing as it cooled, then speeding up again under the influence of mysterious dark energy. As this model matured, the simple linear law Hubble first proposed gave way to a more complex, relativistic version. The relationship between redshift and distance was no longer a straight line, but an accelerating curve. Each new observation of deep space seemed to push the galaxies faster and farther away, as if the very fabric of the cosmos were stretching unevenly beneath our feet. In this modern picture, the universe does not merely expand, it accelerates. The farther a galaxy lies, the faster it recedes, until, beyond a certain distance, its apparent speed exceeds that of light itself. These regions are said to vanish forever beyond our cosmic horizon, carrying their stars, their light, and perhaps their civilizations into permanent invisibility. The universe thus becomes a growing isolation, a mosaic of unreachable islands adrift in an ever-accelerating sea. The numbers themselves defy intuition. Using the relativistic form of the Hubble constant, cosmologists now calculate that galaxies more than 14 billion light-years away are receding faster than light, and that the observable universe expands by over 200,000 kilometers per second at its edge. What began as a proportional, mechanical law has become a runaway geometry, in which even space and time appear to lose meaning. For us, as inhabitants of this expanding frame, the implications are profound. In such a cosmos, the future is bounded not by time but by distance. Whole regions of the universe are forever cut off from one another, their light eternally redshifted, their presence diluted into invisibility. The ultimate fate of such a universe is not collapse but silence, an ever-thinning field of radiation fading into darkness, where energy remains but information is lost. It is a magnificent vision, yet also a profoundly unsettling one. It describes a universe that began in an explosion, races outward beyond the speed of light, and ends not in reunion but in isolation. And all of it rests upon the interpretation of a single phenomenon, the redshift of light. The relativistic redshift anomaly. Although the modern version of cosmic expansion, with its idea of an accelerating universe driven by dark energy, seems to stand on solid observational ground, in reality there is a deep and largely unacknowledged anomaly at its core. This anomaly lies not in the data, but in the interpretation of that data, specifically in the use of the relativistic Doppler formula where the classical Doppler relation should have applied. Every known form of wave, sound, water, or light follows the same fundamental rule. When a source and observer move relative to each other, the frequency changes, but the speed of propagation through the medium remains constant. This is the simple, conventional Doppler principle. It is linear, physically transparent, and entirely sufficient for describing the frequency shift of electromagnetic radiation across all measurable scales. The introduction of the relativistic redshift, however, replaced this straightforward relationship with a nonlinear one derived from the Lorentz transformation. This single alteration, though mathematically elegant, distorted the physical interpretation of cosmic redshift. It produced apparent recessional velocities that grow far beyond the true physical limits of light and inflated the inferred distances and expansion rates of the universe. In effect, the substitution of the relativistic for the classical Doppler shift introduced an error of cosmic proportions, one that makes Hubble's early measurement uncertainties look almost trivial by comparison. The Doppler effect, first described by Christian Doppler in 1842, explains how the frequency of any wave changes when its source moves relative to the observer. The same principle applies equally to sound and to light. When the source moves toward the observer, the waves are compressed and their frequency increases. When it moves away, the waves are stretched and their frequency decreases. In both cases, the effect is purely mechanical, a direct consequence of motion between source and receiver. Later theorists re-expressed this behavior in mathematical form to fit the postulates of relativity, but the underlying phenomenon remained the same. It was an observable change in wave frequency, not a new property of space or time. The Great Distance Divide. When we measure light from a distant galaxy, what we actually observe is a shift in frequency, a reddening of its spectrum. That's a fact of measurement, not interpretation. The question that defines modern cosmology is what this redshift means. Under ordinary Doppler reasoning, such a shift simply tells us that the source is moving away through a medium at a certain speed. Using Hubble's constant, 70 km per second for every megaparsec, we can directly convert that velocity into distance. For example, a galaxy roughly 1 billion light-years away would be receding at 21,500 km per second. The mathematics is simple, linear, and physical, motion through space at a fixed transmission speed, the same way sound waves travel through air. But in relativistic cosmology, that same observation is interpreted very differently. Here, redshift is no longer the signature of motion through a medium, it is said to mark the stretching of space itself. The formula changes, the assumptions multiply, and the results expand almost beyond comprehension. A redshift of 14, the value assigned to some of the faintest galaxies seen by the James Webb Space Telescope, is said to come from a time just 300 million years after the Big Bang, a distance of more than 30 billion light-years away. Two theories, one observation, yet their answers differ by a factor of 30 in distance. In modern cosmology, a single redshift yields two distances. The look-back distance tells us how long the light has been on the road, about 13 to 13.5 billion light-years for sources at 14. But because space itself is thought to have stretched during that journey, the present-day distance to those same objects is over 30 billion light-years. JWST's record galaxy AT is a clear example. Its light has traveled tilde 13.4 billion years, yet today it sits tilde 33.8 billion light-years away. The map grew while the traveler moved. Is this view of space and time acceptable? When examining such claims about space and time, it may be wiser to look not only at the mathematics but at the mindset that encourages abstraction without constraint. In modern cosmology, layer after layer of hypothesis has been built upon earlier theoretical constructs, each defended by further calculations rather than by direct measurement. The result is a structure so internally consistent that it risks losing contact with objective reality, replacing physical cause with mathematical necessity. Theories of this kind may be impressive in scope, but they often drift into metaphysics under the guise of precision. How augmented Newtonian dynamics, and theory, explains cosmic expansion without stretching space. In augmented Newtonian dynamics, this difference is not a triumph of precision, it is a warning. The redshift we see is real, but the interpretation that turns it into cosmic expansion is not inevitable. If light travels through a medium, the photon field or dark matter ether that fills the universe, then its slight loss of frequency over immense distances can be explained without invoking a stretching universe. The velocity of light remains constant, the medium remains real, and the cosmos need not be expanding at all. Redshift revisited under augmented Newtonian dynamics and theory. It is often said that redshift occurs because a wave is stretched as space expands or as a source moves away. But in augmented Newtonian dynamics, this image is physically incorrect. A light wave is not a ribbon being pulled longer, it is a succession of discrete photons, each emitted at a definite instant and position. As the source and the observer move relative to one another, each new photon is emitted at a slightly different distance than the one before it. The change in timing between emissions, not the deformation of an existing wave, creates the difference in frequency that we observe as redshift or blueshift. In this framework, the speed of propagation through the photon medium remains absolutely constant. What changes is the measured shift in frequency. The observed wavelength is therefore a record of emission timing, not a relic of a stretched spacetime geometry. In and theory, therefore, whether we are listening to a receding sound or watching receding light, what reaches us is the latest and longest wavelength pulse that was released, a continuous record of changing emission rhythm, not of any alteration in the speed of propagation, and certainly not a phenomenon that stretches the whole wave. Conclusion: a universe of continuity, not catastrophe. The story of cosmic expansion began with a simple observation, a faint reddening of light from the galaxies. From that single clue, an entire cosmology was constructed, the standard model of the universe, complete with a phase of inflation, a fiery Big Bang, and a present-day acceleration that drives the galaxies apart faster than light. It is a story of grandeur but also of unease, a universe born in violence, stretching beyond comprehension, and destined for silence in the cold geometry of its own expansion. Augmented Newtonian dynamics and theory restores simplicity and physical coherence to this vision. It does not deny the redshift, it reinterprets it. Light does not stretch with space, for space itself is not merely a field but a fabric, a sea of virtual photons forming the background of existence. Within this photon fabric, every quantum of light maintains its speed, its integrity, and its continuity. What changes is not the geometry of space but the energy relationship between matter and the medium through which light moves. Redshift, in this view, becomes a record of interaction, not a measure of recession. In this light, the universe began with an inflationary epoch, just as in the standard model of the cosmos. Where the two theories differ is in their interpretation of what underwent inflation. The standard model claims that it was space itself that expanded, whereas an theory holds that it was energy, compressed to inconceivable density and pressure within the singularity, that underwent inflation, delineating the size of the universe and filling it with light. By the time inflation ceased, that light had transformed into virtual photons, forming the background fabric of the universe, what we know today as dark matter. It was the presence of this omnipresent medium that enabled matter to form during the secondary release that followed the inflationary epoch, the event we call the Big Bang. This vision describes a sequential, continuous transformation, energy becoming form, light becoming matter, equilibrium eternally seeking restoration. The primordial release was not a detonation into nothingness, but the unfolding of an already present continuum, the awakening of potential into visible reality. Thus, an theory offers not merely an alternative cosmology but a restoration of physical meaning. It replaces abstraction with mechanism, paradox with process, and metaphysics with measurable cause. The universe becomes again what Newton and Maxwell once imagined it to be, a living continuum of motion and energy, infinite in extent and transparent in its laws. Perhaps, in the end, what we call the expansion of the universe is not expansion at all, but communication, the endless dialogue between light and the photon fabric that carries it, a conversation written across the ages in the language of frequency and time.